Welcome back everyone. In the last lecture, we came up with the relationship between location of poles and stability of a system. We found out that a system is BIBO stable if all the poles of the system are on the left half of the complex plane. A system is BIBO unstable if at least one of the poles of the system is on the right half plane. If you have poles on the imaginary axis which are not multiple poles, that means at the same location you have only one pole, then you can avoid some specific kind of bounded inputs to the system. If you avoid those specific inputs to the system, then the system will behave like a stable system. However, if you have multiple poles on the same point on the imaginary axis, then the system is guaranteed to be unstable. So, what we will do is we will try to find out an easy way of finding out the location of the poles of a system. We do not have to find out the exact location, only we have to check whether it is on the left half plane, whether it is on the right half plane, or whether it is on the imaginary axis. Let us go ahead and look into that method. So, suppose you have the characteristic equation of an nth order continuous system with transfer function Gs equal to ns by ds. Basically, what it means is that suppose you had a system, suppose G1, then you had this closed loop system, say H, and then you had this, suppose this closed loop system you had, and you did a conversion of this and made it into one transfer function which is Gs. Okay. So, in this case Gs will be equal to G1 by 1 plus G1 H, right. So, suppose this is the system that you got. So, this transfer function will have a denominator, and that denominator is called the characteristic polynomial of the system. So, that characteristic polynomial equation say is this. So, ds equal to, this is the equation, and we know that the roots of this equation, which is also called the characteristic equation, the roots of this equation will give you the poles of the system. In this case, poles of the closed loop system that I had just now drawn. Our question is, how do I find out whether this system is stable or unstable? For which we will have to know the location, the area in which the poles of this system or the roots of this equation are present. See, now what we will do is we will use a mathematical tool. The question came from a system. We had a system, we wanted to know whether this system is stable or not. For that we have to check whether the characteristic equation have roots on the left half plane, right half plane, imaginary axis. Where are the roots of the characteristic equation, that we have to find out. Now it has turned into a mathematical question. Basically, you are given an equation and we are asking when will this equation have roots on the left half, right half, or imaginary axis of the complex plane. So, it is a maths question now, and we have a mathematical tool to find that. A nice one, a easy one. We do not have to find out the actual roots. By using this method, we will be easily able to find out the location. So, here is the method. First of all, you will have to form a table of this form. So, what is this table like? Suppose this is the polynomial that you have. So, let me just take an example here. Suppose you had this. Suppose this is the polynomial that you are dealing with. So, you will start off with the highest degree. So, highest degree is s to the power of 4 here. So, you will start off with s to the power of 4, and then you will fill the row corresponding to s to the power 4 with the coefficient of the alternate terms. So, s to the power of 4's coefficient, then s square's coefficient. In this case there is no square. So, let me just write it like that, 0 s square plus 2s plus 1. So, square coefficient, then the next. So, alternative term. So, an, then an minus 2, and then an minus 4, and so on. The next row will be for s cube in this case, or the next monomial that you have, and then again alternate terms you put the coefficients. Once you have written the coefficients, now we will fill it up. So, it will look like this, s to the power 4 s cube, the next row will be called s square, the next one will be called s to the power 1, then the last one will be called s to the power of 0. This is how we will go down. So, the first two rows we have already filled up using the coefficients of the characteristic polynomial. Now, how do we fill up the next row? Now, here B1 will be nothing but this quantity multiplied by this minus an multiplied by this divided by this. You see, an 1 minus 1 into an minus 2 minus an into an minus 3 by an minus 1. Okay. What will be B2? B2 will be this quantity multiplied by this quantity minus an into an minus 1 divided by an minus 1. Okay. So, this is how we will write down the quantities. What will be C1 then? C1 will be this multiplied by this minus this multiplied by this divided by B1. C2 will be B1 multiplied by this minus this multiplied by this divided by B1. So, this is how you keep on building the table, and then we can use this table to find out the location of the poles or the roots of the polynomial that we are dealing with. So, here is what the Routh-Hurwitz criteria says. Routh-Hurwitz criteria states that the number of roots of the characteristic equation with positive real parts, that means the roots of the equations which are in C plus, is equal to the number of changes in sign of the first column of the Routh array. So, this is called the Routh array. Once you have formed this, go to the first column, this is the first column, okay, go to the first column of the array, look at the number of sign changes that are there, and that will tell you the number of roots of the equation which are on the right half plane. Okay, very straightforward. So, let us take an example and look at this. Here is an example. So, we will first form the Routh-Hurwitz table. So, it will start at s cube. So, you have 1 here, you have 12 here. So, 1 and 12, and then you have 6 here and 8 here. Okay. So, then 6 into 12 minus 8 divided by 6 will give you this term, right. And what about this term? Since nothing is here, so you can replace it with 0, because for this term we would have needed some terms here, right, that is not there. So, this will become 0. What will be this term? This term will be this multiplied by this minus this 6 into 0 divided by 64 by 6, which is nothing but 8, right. So, this is how you form the table. Now, once you have formed the table, now you just look at the first column here. Are there any sign change? No. No changes of sign in the first column. So, that means all the roots of this equation have negative real parts. Okay. Here is another example. Okay, I take another example, I go ahead with the same thing. So, we have 1 and 2 and then 1 and 24. So, we have this as the table. This is the table that we get. You finish this, then you will get it. So, 1 into 2 minus 1 into 24 divided by 1 minus 22. Then the last is minus 22 into 24 divided by 1 into 0 by minus 22 is 24. So, this is what we get, and now you can see that there are 2 sign changes here. So, therefore, this means that there are 2 roots of this polynomial with positive real parts. Now, as soon as you see, now we know that there are 2 roots in C plus. So, 2 roots are in C plus. Now, this is a third degree polynomial. So, we know that there are 3 roots. Where will be the third root then? The third root will be in the left half plane. Okay. So, this is, see, directly you can tell the location of the pole. So, with now suppose this was the characteristic polynomial of a closed loop transfer function. Will this system be stable? No, because you have 2 poles on the right half plane. Whereas, if this was the characteristic equation of a closed loop transfer function, this system will be stable because all the poles are on the left half plane. So, it has 3 poles, all the 3 poles are on the left half plane. Let us take another example. Now, in this example, I have filled up the entire rows again. See, whenever you have nothing to write, you can write 0 here. So, that will make your life easier. You can keep it blank also, it is up to you. So, this is what we get. Now, from here, what can we infer? See, directly you can infer how many sign changes. This is a positive to negative 1 sign change, and from negative to positive another sign change. So, there are 2 sign changes. So, which means that there are 2 roots of the characteristic polynomial on the right half of the complex plane, and we know that this has 4 roots, right. So, where are the other 2 roots? The other 2 are on the left. Now, here is another example. Okay. Now, in this example, one important thing you can also do is that, so for in this example, if I write down the coefficients, this is what I get, right. Now, here you see, in this case 2, 4, 10 has a common factor 2, right. You can actually divide them up. You can divide and make it smaller also. You can do this till the point you do not bring any change in the sign change. If you bring sign change, you are forcing sign change yourself, right. You should not change the sign. If you are not changing the sign, then there is no problem. You can actually go ahead and multiply it with 100 also, all the terms, no problem. Okay. All the terms have to be multiplied with 100 then. So you can multiply anything, you can divide with anything unless you do not bring a sign change. So you cannot multiply with -1, because if you multiply with -1 all these terms, then you are bringing a sign change, right. So which means you are forcing a sign change, which you should not do. So what I can do is, instead of writing 2, 4, 10, I can write 1, 2, 5 also, because I can divide these two terms, these three terms by 2. So this is what I get. Now you see, if I go ahead and go to the next step, I will get a 0 here. Now what is the problem with a 0? Now you see, if I get a 0 here, the problem is that in the next term, this term will be 0 into 2, 0 into 2 minus 1 into 6, right, divided by 0. Now there is a division by 0, which is a problem. So division by 0 is a problem, so we will not divide by 0. So how do we proceed from this point? So if you get such a case where only one element is 0, this element is not 0 however, so only this element is 0, so only the first element here comes out to be 0, then what to do? If the entire row comes out to be 0, that's, we will have to go for a different procedure. In this case, the entire row is not 0, only this element is 0, and that is why you are not able to proceed to the next step. So the best thing is, you can, there are two methods to complete this, but I will just go with one method. Okay, I will give you the name of the other method, you can go ahead and look it up. Okay, so instead of 0, what I will do is, I will use epsilon here, where epsilon is a small positive number. So here epsilon is a positive number, small positive number. Okay, epsilon is a very small positive number, we will use that. Now once we have an epsilon here, I can go ahead and write this, right. So what will this be? This A will be what? A will be 2 epsilon minus 6 by epsilon, but that is nothing but this expression, 2 minus 6 by epsilon, right. And similarly, what will be 5? 5 will be 5 epsilon minus 1 into 0 by epsilon, so that is 5 only, right. So now what will be the next term? So now I can go ahead with the next term. So the next term would be 6 into A minus 5 epsilon by A, right. So 6 into A minus 5 epsilon by A, epsilon you can put from here, and this is the expression that you will get. And finally, the last one will come out to be 10, because B into 5 by B, this should have come out to be 5, right, no problem, this should have come out to be 5 instead of 10, but anyways there is no sign change, so no problem. So this is what you get. Now we check whether the poles are on the left, right, or wherever are they. Let's see. So first, here we are assuming that epsilon is positive. Now as soon as you assume that epsilon is positive, you see what happens. If epsilon is a positive number, and that to a small positive number, then you see 2 minus 6 by epsilon will be a negative number. This is a negative number then, right. You can check this, right. So this is a it's a negative number. And what about B? B in this case, since this is a positive number, this is 6 minus 5 epsilon by A. A was a negative number, so negative becomes positive, and this is a positive number, so this entire term is a positive number now. Okay, so in this case, that means this was positive, this is negative, this is positive. So there are two sign changes, hence two roots have positive real parts. Fine. So if there are two roots which have positive real parts, what can you say? So C plus, we have two roots, then this is a 5-degree polynomial, so C minus, in this case at least will be 3. Okay. Next we consider another case. Okay, suppose this is the polynomial that you have, okay, and you see we are getting 1 1 1 and then 3 3 3, so 3 3 3 can be replaced by 1 1 1, because I can divide by 3, but now is another problem. Now the problem is not, in the last example the problem was only one element was 0, the rest had values, but in this case this entire row comes out to be 0. Now even if you put an epsilon here, you will not be able to solve the problem. Okay, so if an entire row comes out to be 0, then there are many more informations which are which can be taken out from this arrays. So let us try to understand that. So first question is, when does this happen? Will it happen always? No. This happens only when an even polynomial is a factor of the original polynomial. So basically what it means is that this polynomial can be written as multiplication of two polynomials. Out of these, one of the polynomial is an even polynomial and the other one is just QS by PS, whatever you get. When this is the case, when you can factor out from this polynomial you can factor out an even polynomial, you will always end up in a situation where you will have a 0 row. Now, how do we deal with this? Now, to deal with this, this is what we will do. You return to the row immediately above you, okay, which was this row, and form the polynomial corresponding to that. Now, what is the polynomial corresponding to that? This is 1, this is s to the power 4 row, right? So, this is 1 s to the power of 4 plus 1 s square. Remember, the coefficients are alternate coefficients, and this one will be 1 into 1. So, the polynomial is s to the power of 4 plus s square plus 1. This is called an auxiliary polynomial, okay. And this auxiliary polynomial is the polynomial which is a factor of the original polynomial. So, I already said, right, when will you get a condition when the entire row is 0? You will get a condition when the entire row is 0 when the given polynomial can be written down as multiplication of two polynomials where one of the polynomial is an even polynomial. Now, in this case, we can actually find what that even polynomial is. That even polynomial is nothing but the polynomial which you can create just by going one step above, one row above the 0th row. So, this is the polynomial which is a factor of this original polynomial. Now, look at this polynomial. So, that means, see, whenever you get a 0 row, what can you confirm? You can confirm that there is an even polynomial which you can find out from the previous step. Now, that if this is an even polynomial, so polynomials of this form, okay, even polynomial means the polynomials which starts with even degree and then it skips 1 degree. So, all the monomials present, these are called monomials, s to the power of 6, 4 s to the power of 4, 3 s square plus 1. This is an even polynomial, okay. So, when you have an even polynomial, if you look at the roots of such a polynomial, the polynomial roots will always have a structure. What are the structures that it can have? One of the structures that it can have is, suppose in this case, there are 4 roots, right. So, the 4 roots may lie in this way. See, first of all, if this has 4 roots, one of the roots is on the left half, its complex conjugate must also be there, right. Similarly, if one of the roots is on the right half, its complex conjugate will also be there. What is important about even polynomial is that they will be symmetric about both the real and the imaginary axis, okay. This is not just the only case. Instead of this, this might also happen that all the poles lay like this. This is also, see, this is also symmetric about the imaginary and the real axis. We know that the roots are always symmetric about the real axis, but if the polynomial is an even polynomial, then it has to be symmetric about the imaginary axis as well, okay. Can it be an odd polynomial? So, someone can ask, oh, why in this example, since the 0 row came at this point, so you are saying that the polynomial is an even polynomial. What if the 0 came here and then I had some values here? I mean, that can also happen, right. What if the 0 came here? So, in that case, if you go back, the polynomial that you will get is the polynomial corresponding to this. Say, suppose you got as cube plus bs. So, in this case, so then this is a factor of this. Now, if this is a factor of this, you notice that if it is an odd polynomial, you can always take out an s. You can always take out an s, right. See, then this polynomial can be written as s into as square plus b into whatever is left, right. So, then also you see an even polynomial is a factor. So, that is why, I mean, even if your s cube row, s square row becomes 0, then also it is not a problem, and even polynomial will always be a factor, okay. Now, how does it help us? You see, we started this entire idea of Routh-Hurwitz criteria to know the location of the poles, right, whether it is on the left half or whether it is on the right half. So, let us finish that, and also we will see that this will also give us more information. So, how do we proceed? We are stuck at this point, right, because we got a 0. So, the idea is you find out the auxiliary polynomial. Again, I am repeating, the auxiliary polynomial is a factor of this polynomial, the original polynomial. Then you do replace the all 0 rows, that you have, replace it with the coefficient of DDS PS. You take the differentiation of this with respect to s, then it becomes a 3rd degree polynomial. It will come down by 1 degree. So, this is the polynomial that you get. So, the 0, 0, 0 that you got here, you replace that by 4 and 2, okay. But again 4 and 2 is divisible by 2. So, I can also replace that by 2 and 1. Here I have not done that. If you want, you can do that. Now you see, once you have made it 4, 2, 0, now we can again continue, right? We are not stuck. So you again go back to the same thing, 4 minus 2 by 4, which is half, and then we have 1, and then you finish the entire table. Same method. Now what is important here is, how do we now infer about the position of the poles? Now here is what we will do. You see, I have already said that PS is a factor of QS, right? This auxiliary polynomial is a factor of PS. So that means PS divides QS. Now what is PS? PS, you see, PS in this case is 4th degree, right? So if I would have started with PS, this is the point I will have to start with. So 1, 1, 1, 1, 1, 1, right? So this part, because the first column is what is important for us, this part corresponds to the auxiliary polynomial. Okay. So this part, sign changes and everything will give me idea about where the location of the auxiliary polynomial roots are. Now if I, then what is the other part? So QS was there, right? This was the original polynomial. So QS by PS, whatever is left is the rest. So this part corresponds to QS by PS. Okay. So what do you mean by that? So if I just look at this part, s to the power 5 and s to the power 4, there are no sign changes. This means that the polynomial QS by PS, the roots of polynomial QS by PS are in C minus, because there are no sign changes. Now see, I have written here. So for QS by PS, there are no sign changes, and see, QS by PS in this case is degree 1, right? Because PS is 4th degree. So QS by PS will be degree 1. So there is only one pole, and that pole is on the left half of the complex plane, because there is no sign change. Now we talk about PS. Okay, we will talk about PS now. So to talk about PS, we will look into only this part, and here you see that there are how many sign changes? There is 1 and 2. There are 2 sign changes. So 2 sign changes, you see, first of all, one thing that you know about PS, I am inferring about PS now. The one thing that you know about PS, it is an even polynomial. So if it is an even polynomial, it has to be, the roots of this polynomial must be symmetric about the real and the imaginary axis. If it has to be symmetric about the real and the imaginary axis, the pole locations can be like this, because there are 4 poles, or the other option can be that they are like this, or they can be on top of each other also in this case. Now in this case, we have found that there are 2 sign changes. Now if there are 2 sign changes, we know that there are 2 roots on the right half plane. If there are 2 roots on the right half plane, so this is not possible, right? This is not there. So if this condition is gone, and if there are 2 roots on the right half plane, because it has to be symmetric about the imaginary axis, the other 2 must be on the left half plane, and that is what I am writing here. So as a whole, there are 3 poles on the left half plane and 2 poles on the right half plane, or roots on the right half plane. You see, let me take another example. Okay, I mean, the more examples you take, more clearer it will become. Okay, so let me take another example. So here is another example. This is a big one, 8 degree polynomial, and these are the coefficients, the first 2 rows. And you see the second row here, 3, 24, 96, 192 can be divided by 3. So I have divided by 3, and this is what I get. Then you go to the next row, you do these calculations. I have already discussed how to do that. So this is the row you form. Again, this is divisible by 2. So I divide by 2, and this is what I get. This is nothing, so I can write 0 here. So this is what I get. Now you see, you can see that these 2 rows are similar to each other, which is equal to each other, which means that if you do the calculations, you will get 0 row. As soon as you get a 0 row, you go back to the previous row and form the auxiliary polynomial, and the auxiliary polynomial in this case will come out to be s to the power of 6 plus 8 s to the power 4 plus 32s square plus 64. Okay, then you do differentiate this polynomial with respect to s, and this is what you get, 6, 32 and 64. You replace the zeros with 6, 32 and 64. Again, this is divisible by 2, so you divide by 2, and this is what you get. You may not even want to divide by 2, it's up to you. But even if you make such changes, remember that do not introduce sign changes on the first column. If you introduce sign changes, you are forcing a sign change, that you should not do. So 3, 16, 32. Now we go to the next level, which is 8 into 3 minus 16 by 3. So 8 in 24 minus 16 by 3. This comes out to be 8 by 3. Again, this is what I get. Now in order to simplify things, see, I can do what? I can multiply this entire row by 3. because I am not bringing sign changes. I multiply the entire row by 3 and then divide by 8, and this is what I get. So, basically I am multiplying by 3 by 8. If I multiply everything by 3 by 8, it becomes simpler, that's it, the calculations become simpler. So, this is what I get, and then I keep on continuing this same method, and finally I end up in this table. Now, once I get to this table, now I can infer about the different polynomials. Okay. So, how can I infer about PS? So, I have to infer about the signs of the roots of PS by looking at, so this is s to the power 6. So, from this point to this point will give me information about PS, and from this point to this point will give me information about QS by PS. Okay. So, let us infer about PS. So, in this case, first of all, there are 6 roots here, and you see there are 2 sign changes, right. If there are 2 sign changes, I know that there are 2 roots on the right half of the complex plane. Now, if there are 2 roots on the right half of the complex plane and this is an even polynomial, there must be 2 roots on the left half of the complex plane also. This is due to the symmetry that we have talked about. So, 2 and 2, but this is a 6-degree polynomial, right. So, there must be another 2 poles. Now, where are those 2 poles then? They must be on the imaginary axis. So, you see, by simply deducing just by sign changes, I can actually go ahead and tell the entire distribution of the location of the poles for PS. Now, for QS, you go back to these 3 rows. In the first 3 rows, there are no sign changes. That means all the roots of QS by PS must be on C minus, and you get it 2. So, you see, so what is the distribution? 2 to 4. So, here is, I have directly given another example here also, same thing. So, in this case, there were no sign changes for QS by PS. So, there is only one pole on the right, and in this case, there are no sign changes. This case is interesting in the sense that you see, for this part, for this PS part, there are no sign changes, right. Now, if there are no sign changes, that means you cannot say, see, in general what we would have said, if there are no sign changes, we would have said that this polynomial has all its roots on the left half plane, but that is not true, right, because if it has roots on the left half plane, it must have roots on the right half plane also, because it is a even polynomial. So, that case is not possible in this case. So, the only possibility therefore is all the 4 roots are on the imaginary axis. This is the reason this example has been given. So, I mean, just if you look at this part of the row, there is no sign change, or directly you can say that means all the poles of PS must be on the left half plane, but how is that possible? PS is an even polynomial. If it is an even polynomial, all the 4 roots cannot come on the left half plane. Oh, does that mean that 2 are on the left and 2 are on the right? But that is also not possible, because if the 2 are on the right, there should have been a sign change here, right? That has not come. So, what is the only possibility? So, the only possibility is that all the roots are on the imaginary axis. Okay. Now, this brings us back to this problem that we had discussed for root locus. Okay. So, I hope that you have understood the method of Routh-Hurwitz criteria by now, like all the steps I have given you examples, try with your own, you can create your own polynomials. So, generally what I do is that I take up some poles, distribute it over the complex plane, and then create the polynomial for that. And once I have the polynomial, I practice with the help of Routh-Hurwitz to see the distribution, to understand how it looks like. You do 2, 3, 4, 5 examples with it, it's fine. After that, it will become very easy. Okay. Now, I want to come back to the root locus problem, that example that we took. And I remember, I think it was 2 lectures back, I guess. Remember, I had already told you that to find out the point on the imaginary axis, I will come up with a better plan, a better method. Okay. And that method we have already learned actually. I will show you how to use it. Okay. So, what are we looking at? We are trying to find out the point where the root locus cuts the imaginary axis. That is what we want to find out. This was the problem that was given to you. We had found out all these points. I have left out the imaginary axis point here. Okay. This we had already done, and we already know the actual answer was 1.09 because I had already written the answer. But how did I get to the answer? First of all, in this case, what is the characteristic polynomial of the system? The characteristic polynomial of the system is k gh equal to 0, right? K gh equal to 0. So, this is the characteristic polynomial of the system, and we are trying to find out when will this polynomial cut the imaginary axis. So, this is the characteristic polynomial of the system. The characteristic polynomial comes out to be this, because ns by ds is nothing but this. So, if you write down, this is the characteristic polynomial. Now, if this is the characteristic polynomial, I can write down the Routh-Hurwitz table. So, the Routh-Hurwitz table will come out to be something like this, okay, because for this what is this 1 8 k 1 8 k and then 5 and 6 5 and 6 you write down, and finally this will be what it is. Okay, go ahead and write this. Now comes the main part. Here k is variable, right? So, first of all, how many closed loop poles does this have? How many roots does it have? 4. So, if it has 4 roots and we want that if the roots have to be on the imaginary axis, you know that the one of the rows must go to 0, right? Because if the roots have this structure, which is basically symmetric about the real and imaginary axis, an even polynomial must be a factor of this. Otherwise, this is not possible. When is an even polynomial a factor of this? One of the rows in the root locus on the Routh-Hurwitz array must go to 0. These 3 rows cannot go to 0, right? Because these are constant numbers. The only 2 possibilities are you make this row go to 0 or this row go to 0. Now, how do I make this row go to 0? You have to take k equal to 0, but k equal to 0 is this point, right? K equal to 0 is the starting point. So, k equal to 0 is not, because we already know where k equal to 0 is. K equal to 0 is starting at this point. So, the only possibility is that if you make this equal to 0. Now, if you make this equal to 0, k will come out to be 8.16. So, which means that if you plug in 8.16 here, this row becomes 0. This will become 5 into 8.16 because this goes to 0. So, now you see you have a case when the entire row is 0. The entire row is 0. Now, if the entire row is 0, you go back to the previous row and write down the auxiliary equation, which is 34s square plus 5 into 8.16, right. This is the auxiliary equation. Basically 34s square plus 5 into k was 204 by 25 this. Now, from this you see this is a even polynomial and we know that this auxiliary equation will be a factor of this then. So, I just have to find out the roots of this, right. What are the roots of this? The roots of this is s square plus 1.2 equal to 0, which is s equal to plus minus 1.09. So, that means at this point the value of k is 204 by 25 and the point of intersection is plus j 1.09. See, I have used the Routh's table to come up with the point at which the intersection happens. Okay. So, this was the part which in the puzzle which was left, and this is how you can find out the imaginary point intersection of for the root locus case as well. So, in this lecture we have covered a lot. We have seen how to find out the distribution of the roots of a characteristic polynomial or the poles of the system on the complex plane, and we have also used the same method to find out imaginary axis intersection points for the Routh-Hurwitz case also. I will take everything together now and move ahead with using the root locus for design of controllers which meets the specifications that we want, okay, and that will be part of the next lecture. Thank you.